Trigonometrics. So today we have taken one question from gravitation, where two satellites are there, S1 and S2. So the two satellites in front of you are, and this is a S1 and S2 revolve around the planet. So if this is the planet, let us say the planet is circular in shape, and the two satellites which are revolving around it are S1 and S2, right? Let us say S1, the first satellite over here, and S2, the second satellite over here. And as per the question, that these two satellites S1 and S2 revolve around this planet in a coplanar circular orbits in the same sense, and their orbits of revolution are 1 hour and 8 hour. So in the same sense, that means the direction of movement of both the satellites are same, right? Let us say this is the orbit of S1, and let us say this is the orbit of S2, right? So you can say that these both of the satellites are moving into the same sense, that is the same direction of movement is there. Okay, so these are the orbits. So orbit of satellite 1, orbit of S1, and this is the orbit of S2, right? Now as per the question, it's given that the period of revolution are 1 hour and 8 hour. So for S1 period of revolution, so we can say for S1 the T1 is given to you, and for S2 T2 is given to you, right? So the value of T1, that is the period of revolution, T for time, are 1 hour and 8 hour respectively for first and second satellite. So this is 1 hour and this is 8 hour, right? So this is the data given to you. Now what we need to find, we need to find that the radius of orbits of S1 is 10 power 4 kilometers. So it's also given that the radius of the orbit of S1, right? So we can say R1 is nothing but 10 power 4 kilometer. 10 power 4 km is given to you. So this is for R1, this is for R1, and for R2, it's not given. What will be the angular speed of S2 as observed from S1? So we need to find the angular speed of this S2. So we need to find the angular speed of S2 with respect to S1. This is the question to us, right? This is the question to us. Now the average speed of S2 with respect to S1 we need to calculate. Now we know that by Kepler's law, if you remember, the time period of revolution of a satellite around a planet, a square of that is proportional to radius of the orbit of revolution and cube of that, T square equal to R cube, right? Has Sagi. So this relation we know that, right? Applying this relation, we can write that the ratio of T2 to T1 square can be written as R2 by R1 whole cube, where R1 and R2 are the radius of the orbits of both the satellites, right? R1 and R2 are the radius of the orbits of both the satellite S1 and S2, right? This relation is right. Now we need to find the average speed of S2 with respect to S1, and not average, basically it's angular speed. Angular means V equal to R omega, you know that, right? And omega is the angular speed. So we will find the radius first. Okay, so just put up the values over here. Okay, just R2 by R1 whole cube, this is the relation given by T2 by T1 whole square. and time period of revolution of T2 is 8. So just put up the value of 8 in place of T2, in place of T1 write 1, because it's given that 1 hour and 8 hour for T1 and T2. This is whole square, right, is equal to R2 by R1 whole cube, right, and R1 is given to you. So what we'll do, 8 into 8, 64, 64 into 10 power 4 kilometer. So what we will do, 64, 64, just leave it, 8 square 64 equal to R2 by R1 whole cube. So RT cube by R1 whole cube. R1 is 10 to the power 4. 10 to the power 4 will be multiplied 3 times. So it will be 10 to the power 12. Right? And take the, so R2 is nothing but, R2 cube is nothing but 64 into 10 power 12. Right? And this will be in kilometer. Take cubic root into both the sides of the equation. Take cubic root into both the sides of the equation, then you will get the value of R2. R2 is 4, 4, 16, 464. So it will be 4 into 10 to power 12 will be coming 3 times. So 10 power 4. 4 into 10 power 4 kilometer is the value for R2. This is the value for R2 and this was R1, right? So R2 is 4 into 10 power 4 kilometer. This is calculated. The radius of the satellite. Hi Sagi. Oh, wait a minute in this even. Okay, we will discuss Sagi. We will put up your queries. Okay. So this is the value of R2. Now at this position, let us say the linear speed of satellite 1 is nothing but V1. Let us say this is V1, right? Similarly for satellite 2, the speed over here is nothing but V2, right? Now this relation you can see, if the mass of the satellite is m1 for s1, m2 for s2 and m for the planet, in fact the mass will not be required. We need to understand the linear speeds. So linear speeds are v1 and v2 over here, right? v1 and v2 are the linear speeds, right? So at the closest point of separation, this will be the closest point of separation when they are just close to each other, when s1 is standing just perpendicular to the from the point of center. Okay, let us say this is the center. Okay, now at the closest point of separation, what we can see that they are moving into the same direction, right? Hence the speed of s2 with respect to s1 will be, the relative speed will be v2 minus v1, isn't it? Relative linear speed is equal to v2 minus v1, isn't it? Relative speed. Now what we can do, since we have already calculated the radius, so for the entire orbit 2 pi r is the total displacement, or the total displacement 2 pi r. We know the relation of velocity with respect to the displacement, so that we can write as 2 pi r, we can write 2 pi r by t is equal to v, right? Isn't it? 2 pi r by v is equal to t. This is the displacement, this is the time, and this is the linear velocity, right? Using this relation, we know the value of r1. Okay, for r1 this will be equal to 2 pi into r1 by t1, which will give you v1, right? This will give you v1. So what we will do, the value of v1 will be calculated. So v1 will be equal to nothing but it's equal to 2 pi, and t1 is nothing but 1 hour. You can see t1 is 1 hour. So 2 pi by 1 into r1 is 10 to the power 4, right? So this will give you 2 pi into 10 power 4 kilometer per hour. This is the value for v1. The linear velocity of satellite 1 is 2 pi. You can see 2 pi into 10 to the power 4 kilometer per hour. Now the linear velocity v1 is calculated, and what is the value of v2? Similarly, v2 will be equal to 2 pi r2 by t2, right? And we know the value of t2 is 8 km per hour, right? So just put up this value over here. So t2 can be put over here, and we can see v2 will be equal to 2 into pi into r2. R2 is 4 into 10 to the power 4 kilometer. 4 into 10 power 4 divided by time in hour. So that's why its velocity will be in kilometer per hour. And t2 will be nothing but 8. So just put up these values. You can see 2, 4, 8 will be cancelling this 8, and we get the value of v2 as equal to pi into 10 power 4 kilometer per hour, right? This is the value of v2. So v2 is calculated pi into 10 power 4 kilometer per hour. Now what is the benefit of this? Benefit of this, we get the relative velocity. Relative linear velocity, which is equal to nothing but v1 minus v2 or v2 minus v1, right? So this will be coming as v2 minus v1. This will be coming as the net relative velocity will be 2 pi into 10 to the power 4 minus pi into 10 to the power 4. So this will be giving you relative linear velocity is coming as 2 pi minus pi will be pi. So it will be pi into 10 to the power 4 kilometer per hour. This is the relative linear velocity, that is v1 minus v2 or v2 minus v1. You can take the magnitude of this, right? So this is calculated. So v2 minus v1 is identified, and this is the relative velocity of both the satellites, right? Pi into 10 to the power 4 kilometer per hour, right? Now this as seen from s1, right? This position, the satellite s2 is at a distance of r2 minus r1. So this distance is nothing but r2 minus r1, right? So this relative velocity, when you are going to calculate, right, that need to be taken care. This r2 minus r1 need to be taken care, right? So we know that V is equal to R omega. So the relative angular velocity, I am writing relative angular velocity, relative angular velocity can be written as, since we know that V equal to R omega, I use that relation. So if I'm writing omega as the angular velocity, then it will be equal to V1 minus V2 or V2 minus V1, the magnitude of that divided by R2 minus R1, this one, R2 minus R1. This will give you the relative velocity R2 minus R1. So let us take it V2 minus V1 instead of V1 minus V2. So this will give you the relative angular velocity of what? Satellite 2 with respect to satellite 1. This we need to find. Angular speed of S2 with respect to S1. Right? So here, hi Mike, very good morning. Are we solving the no? We have simply taken the Kepler's third law, okay, and from the time period and radius of revolution of orbit, okay. From here we just evaluated R2, and from R2 we used the simple relative linear speed, okay, and the velocity displacement by time, and from here we calculated V1 and V2. So thereafter the relative linear velocity is calculated, and after thereafter relative angular velocity is equal to V2 minus V1 by R2 minus R1. We are knowing all the values. So this is for relative angular velocity of satellite 2, it will be omega 2, right? We are simply putting up these values, okay. In this way we are solving, right Mike? So here omega 2 can be calculated by, you just put up the value of V2. V2 is pi in 10 power 4 and V1 is 2 pi 10 power 4. So just subtract 2 pi. So V2 minus V1 we have already calculated, pi into 10 power 4. So this omega 2 can be, this omega 2 can be written as V2 minus V1, whose value is pi into 10 power 4. So just put up this value, pi into 10 power 4 kilometer per hour divided by R2 minus R1. What is R2? R2 we have calculated 4 into 10 to the power 4 and R1 is 10 to the power 4, right? So R2 minus R1 is 4 into 10 to the power 4 minus R1 is 10 to the power 4 minus 10 to the power 4. So this will give you the value of omega 2, that is angular velocity of satellite 2. This is for satellite number 2. This is omega 2, which is equal to 4 pi into 10 power 4 divided by, if 10 power 4 will be taken common over here, so 4 minus 1 will be 3, right? So this will be giving you, and 10 power 4 will be cancelled out. So this will be giving you pi by 3 radian per hour. So pi by 3 radian per hour is the relative velocity of satellite 2, the relative angular velocity of satellite 2 with respect to satellite 1. And the answer is, this is equal to pi by 3 radian per hour, right? And in this way we have solved this question, students, right? If you find it useful, you can just be connected, and for any query you just put up into the comment box. I will try to help you, okay? Thank you so much for watching. Take care. Bye bye. Happy learning. Any doubt, students, into the entire solution? Let me know. So in this way we have solved this question, right? Do you want to take it up through the entire stages? This was the question. Planet, two satellites revolving around it, coplanar. That means they are on the same planar. So here we can see some, yeah. So we just, you can see through the steps what we have taken. Time period of revolution of first satellite, time period of revolution of second satellite. R1 is given to you, the radius of orbit of revolution of first satellite, and R2 is not known to you. We use the Kepler's law, T square equal to R cube, and put up the value of time period of revolution of both the satellites, and R1 is known to us. Thereafter we calculated the value of R2. This is 4 into 10 to the power 4 kilometer. After that, what we did, relative linear speed equal to v2 minus v1. Why? If the v2 is the linear speed of satellite second and v1 is the linear speed of satellite first, right? Then the relative will be v2 minus v1 by r2 minus r1. So v2 minus v1 is calculated. How? Because v is not known to us. So velocity is displacement by time. So if they are covering the entire orbit, that means 2 pi r displacement will be equal to 2 pi r divided by time, and 2 pi r is for satellite 1, it will be 2 pi r1 divided by time period of first satellite. So this will give you the velocity of first satellite as 2 pi into 10 to the power 4 km per hour. Similarly for v2, when you replace r with r2 and t with t2, we get the velocity of the second satellite, that is pi into 10 power 4 kilometer per hour, right? In this way, the relative linear speed will be v2 minus v1 magnitude of v2 minus v1 or v1 minus v2. So that will be equal to 2 pi into 10 to the power 4 kilometer minus pi into 10 to the power 4 kilometer. This will give you pi into 10 to the power 4 kilometer. This is the linear velocity, relative linear velocity. Now relative angular velocity, use the formula v equal to r omega. So the for the satellite 2, let us say omega 2 is the angular velocity, relative angular velocity which we are about to calculate. So this will be equal to v2 minus v1 by r2 minus r1. And we have already calculated v2 minus v1, that is pi into 10 to the power 4 kilometer per hour. Just put up this value and into the denominator r2 minus r1. r2 minus r1 is nothing but, we have already calculated r2 here, 4 into 10 to the power 4 kilometer. We are note the value of r1. r1 is given to you, that is 10 to the power 4 kilometer. You can see here r1 is given to you as 10 to the power 4 kilometer. So r2 minus r1, you know the value. Just put up these values and solve, you get the value of omega 2, that is the relative angular velocity of satellite 2 with respect to satellite 1 is pi by 3 radian per hour. And that's why we have solved this question, and this is the answer, pi by 3 radian per hour. For the satellite 2, the relative angular velocity of angular speed of satellite 2 with respect to satellite 1 is nothing but pi by 3 radian per hour, right? So thank you so much for watching, students. Be connected, take care, happy learning, bye bye, see you.